Okay, so just to complete uh, this slide, okay, I'm taking more time to make it easy for you people to understand in the details, okay, and I'm also trying to compare class B with the previous class, which was A, so that we can differentiate between the operation of both. So basically, now uh, so if I draw the Q point, okay, for class B amplifier, so the Q point happens to be over here at the cutoff, okay, somewhere at this point, okay, which is cut off, and this is your saturation, right? Okay, now if I draw the Q point for class A amplifier, so class A amplifier, because of the biasing, okay, because of the biasing at the base, class A amplifier, the Q point was Q, overhead at the midpoint. So it means, if you see, it means that the class A amplifier, okay, okay, has a conduct, this has some value of current which was IC, has some value of current which was, okay, this value of current ICQ. So it means that even if there is no signal present at the input, okay, this amplifier would, class A amplifier would give you conduction. But in class B amplifier, if there is no input signal, so the amplifier remains in Q point, in the cutoff region, okay. Now what we can see, that in terms of power dissipation, in terms of power, how much power, how much power can be withdrawn from this VCC, okay, from this VCC, okay, from the power supply. The question we can ask, that how much power is drawn from VCC, okay. So in power, in class A case, in the case of class A amplifier over here, okay, we can see that your P in DC, if I calculate this P in DC, okay, P in input power from the DC source supply would be equal to VC, okay, from the supply into ICQ, okay. I call this ICQ because this is the current, okay, this much is the current at the Q point, okay. So definitely, okay, if you see, I can see this is VCC, okay, and this ICQ is basically how much, this is IC, okay, this one is IC, okay, as saturation, and this is Q point, okay. So this is IC, okay, divided by 2, okay, because this is at the midpoint, okay. So it means that if this was a class A amplifier and there was no input signal, but still, okay, the amplifier was extracting, this amplifier was extracting a power equal to this value, okay. So under no signal condition, this much power is still being taken by class A amplifier, okay, class A amplifier, okay, okay, this is class A amplifier, okay. This much power is taken from class A amplifier under no signal condition. But okay, when I switch to class B amplifier, okay, with this class B amplifier, when I switch to class B amplifier, now under no signal condition, if I there is no signal present, okay, so the Q point is at the cutoff, okay. ICQ, if you see, ICQ over here is 0, there is no ICQ, ICQ is 0, ICQ is 0. So what happens, that if I put the value, okay, this P in DC, VCC is there, but ICQ is what, is equal to 0 over here, okay, I put it to 0. So my input, okay, power, okay, under no signal condition will be equal to 0. So it means that this amplifier is good amplifier, because it is not, class B amplifier is a good amplifier because this is not extracting any power, okay, or is not withdrawing any power, okay, when there is no signal, okay, because the amplifier is in the cutoff. And class A amplifier, in terms of power input power dissipation, it is in terms of, it is a bad amplifier, you can say, okay, that it extracts this much power, okay, under no signal condition because of the biasing present at the base. Okay, next slide please. Okay, okay, if you see now, so I redraw this line over here. Okay, if I draw this circuit I explained it to you. Okay, this is a typical class B amplifier. Okay, that the amplifier, okay, when the input signal goes in, okay, for amplifier to be operated, this base emitter junction should have a value greater than 0.7 or equal to 0.7. Okay, uh, so what would happen, that whenever the input signal, the positive half cycle, the value of this signal, okay, in the positive half cycle, it gets greater than 0.7, it operates, it conducts. Okay, and when the amplifier goes into this negative half cycle, okay, there is this value is lesser than this 0.7, so it cannot forward bias this junction, so we cannot, the amplifier is off, there is no conduction. Similarly, there is a conduction for positive half cycle, there is no conduction for negative half cycle, and this is again the DC, the AC load line. Okay, so by there is we only discuss that AC load line. There is no DC biasing actually, so you can ignore DC by load line for the time being. Okay, so it means that this is my Q point. Okay, the amplifier is always in the at the Q point, a class B amplifier. Okay, which is at the cut off. This is saturation. Okay, now if I draw the value, the shape of the waveform, so the amplifier can amplify, okay, one half cycle. So you can see from this point, okay, to 0. Okay, so you can see I can draw a waveform like this, so it can amplify one half cycle. Okay, the class B amplifier. Similarly, on the current side, okay, I can draw a wave shape like this, which goes from 0 then to maximum and then further down to 0. So this is a typical waveform or swing or waveform on the AC load line. Now if you compare, if you want to compare this with the class B amplifier, so the class B amplifier, sorry, with the class A amplifier, so in that case, okay, the Q point was over here. Okay, so this was the Q point. Okay, right over here, this was the Q point. So you have an amplifier, okay, have the capability, okay, to operate like from here and then from like this one, this for class A amplifier, this one, because the Q point was at the midpoint. Okay, similarly the current had the tendency to swing, okay, for equal half cycle and then negative half cycle, remember. Okay, so this was a typically class A amplifier. Okay, this was a typically class A waveform which was equally swinging, okay, around this Q point. Okay, this was because the Q point was at the center. Okay, but for class B, we can see only one half cycle, the other half cycle cannot be, there is no conduction for the other half cycle. So in that case, how we can actually quantify efficiency? Okay, efficiency. So efficiency, we look at the efficiency on amplifier is a ratio of two powers, which is P out, we say output power, and the input power. Now the output power should be in terms of AC. Okay, so we say this is AC output power. Okay, and the input power, we can see the input power, that how much the amplifier is getting the input DC power from the VCC. So it should be a DC power. So next we discuss that. Thank you.